transpose x2 transpose. So basically all of our data points laid down on their side into rows. And so basically each one of these xi's is a vector, a column vector in RD. And so then if we wanted to basically d-mean each vector, what we would do is we'd say compute like, we would define, say, mu is equal to 1 over n. Where this, of course, is a vector, a column vector in RD. And then you could also compute the standard deviation. So you could compute sigma squared equal to 1 over n minus 1.
Kevin, am I supposed to be able to hear you?
Yes. Can you not hear me?
I can.
We can. I can hear as well.
Okay. That was terrifying. And now, but we could have computed this as well as looking at the jth component. So mu j is equal to 1 over n, 1 to n of xij, where this is the jth component of the ith example. And then what we could do, we could define the standard variance, or the sample variance, sigma j squared, as xij minus mu j squared. And then to standardize our data, we could define x tilde ij as being equal to xij minus mu j divided by sigma j. And why would we want to do this if we were to stack? So for all ij, set this equal to this. Now we'd have this very nice, this property where the mean is going to be equal to 0, and the standard deviation, sample standard deviation, is also equal to 1. And this could be useful because basically your data could come from various different sources. You know, this could just be a completely different scale. You know, even if you're measuring distances or something, and one of your dimensions was measured in feet, one of your dimensions was measured in inches. Those are just completely different scales, and so just the order of magnitude of the units would just be so different. But that's not really real. That shouldn't really matter in the problem, especially if you're doing like a linear or a polynomial sort of approximation, function fit. So it's very typical to standardize your data, and typically, you know, there's no standard for what standardization means, but typically, when people say standardize your data, that typically means to subtract off the mean of each dimension and then divide by the standard deviation. And so it's somewhat more controlled. It's all sort of like on the same order of magnitude and centered. And the underlying assumption here is that like the mean and the spread of the data has no sort of bearing on the predictability. Like the actual magnitude of these numbers don't matter. It's all about the relationships between the features that matter. And particularly in a linear classifier, this is particularly true because you can invert all this out. It doesn't matter. We'll see that more when we talk about SPV and stuff. When we start really doing transformations of covariance matrices. It'll be very fun. Did I answer the question?
Yeah. So one other thing, the first column is all ones, right? So if we standardize, then like the standard deviation is 0. So what do we do in that case?
Excellent question. Okay, so this is something that we forgot to mention when we were talking about linear regression. So let me just spend a few minutes talking about that. It's worth it because I was trying to find time to do that anyways. So this is a good one.
And for sure, like we did mention briefly this idea that like we might need an offset, but I think we didn't do sufficient justice to that.
Yeah. So suppose that you want to fit a model, you have data.
We can't see the screen.
Thank you. I have no idea why it stops sometimes. So if you suspect that I'm ever drawing something and you don't see it, please let me know. Thank you. Clearly, these tools are not foolproof. So your data is these xi, yi pairs, where each xi is in Rd and each yi is in R. And what we'd like to do is we want to fit a W in Rd and B in R such that yi is about approximately xi transpose W plus B. Okay, this is approximate. We know there's going to be some noise. I'm not even going to make an assumption about where the data came from. I'm just trying to fit some data to it. I'm just trying to fit some linear line to it. So there's a couple of different strategies for doing this. The first strategy, so we want to fit this to least squares. And so what we'll do is W hat B hat is going to equal the argument WB. It's our least squares estimator, like we always do. Right, because our estimated W transpose xi plus B, and we're trying to estimate yi, so this makes sense. And what we saw in Jamie's lecture was that I'm going to go and find it just so I don't write something wrong. It would be really bad if I wrote down an equation that was just blatantly wrong.
It's possible I wrote down something that was blatantly wrong too. So, although you were paying attention, so that means it's less likely.
As anyone who's lectured before, you know that it's very easy to, when you're this close to it, write something that is just wrong and you have no idea. You know? It's
much easier. It's much easier as an observer to see a mistake.
Okay. So there we go. So if you take the derivative with respect to B, what we find is that, right, oh yeah, that's how we do it. So what you'll find is that B hat, with respect to this equation, is equal to what you get. We get this equation that's like x transpose x W hat plus B hat x transpose 1 equals the x transpose y, and where these x's and y's are again stacking all your vectors together. 1 transpose x w hat plus b hat 1 transpose 1 is equal to 1 transpose y. And this is, of course, just writing this as oops. This is rewriting this equation as in vector notation, y minus x w plus b with an all ones vector. These are equivalent formulations, and then just taking the derivatives vector w and b and solving for them. So what we see here, though, is that suppose we had standardized our data before, right? Suppose, like, let's define, suppose we'd say, well, x tilde is equal to, I centered it. So I made sure that x tilde ij, little guy, is equal to x tilde xij minus mu j, where mu j is equal to 1 over n ij. So now my xij's are mean 0. Okay, and I'm also going to define y tilde I as equal to yi minus 1 over n I equals 1 to n of yi in a different index, yk. Now what we have is that the x tildes and y tildes are both mean 0. Okay, now, so why is that important? Because if I form my my same matrices x tilde and y tilde, then these are all going to be tildes. And then what we get is that x transpose 1, this guy here, that's summing up your x's, because the x matrix is an n by d matrix, so x transpose is a d by n matrix, and this 1 is just a n by 1 matrix, and so x transpose 1 is literally just summing up all the sum is doing x transpose and then just summing along the columns, along this way, and so that's going to be mean 0, because by definition we centered everything. So this guy is 0. And for the same reason, this is 0, because 1 transpose x is the same thing as x transpose 1, but that all transpose. And what we get is something kind of amazing, right? Because we get that w hat, if we solve this first equation, we get that w hat is equal to x tilde transpose x tilde inverse x tilde y tilde, and b hat is equal to, this is just equal to n, of course, because each one of these vectors ones is an n by 1 vector, just of all ones, so they sum to 1. And then so b hat is just equal to 1 over n 1 transpose y, which is just summing up all the y's. But we just said that the y tilde is equal to 0, right? The mean of y tilde is equal to 0, so this is actually just equal to 0, which is kind of cool. So, okay, but that's great, but we transformed this data. What did we just do? Like, we just transformed all of it, and that's kind of scary to me. Just for some, I'm going to want to actually define this differently. Or explicitly, I'm going to call this y bar. So Now, what we want to do is actually predict our yi's. And now, so what we're doing, our x tilde I transpose w hat plus 0, basically, is about, we're saying this is about y tilde I. This is our sort of approximation. But we don't want these in terms of y tildes and x tildes, we want in terms of x's. So let's just write it. So then we know that y tilde I is equal to yi minus y bar, which is about xi minus mu transpose w hat. Right, I'm just plugging in my parameters here. And so this implies that yi is about xi minus mu transpose w hat plus y bar. This is a very heuristic way of doing this. It's just intuitively how I think about it when I have to think about, like, okay, how do I do this transformation back? This could be, you can do this more formally in another way. But I just like to think about, like, you just think about intuitively, what did you do? You were trying to predict yi. And so when I demeaned everything, I was trying to predict y tilde I. And so when I just invert everything out, I get this thing here, but this is here. What this is just xi transpose w hat plus, or minus, mu transpose w hat plus y bar. And so if you want to go back to these up here, if I want to run my original b and w, maybe I should call these w tildes, b tildes, just so I'm not confusing anyone. So that could be very. So then what I have here is just equal to xi transpose w tilde plus y bar minus mu transpose w tilde. And so what I'm going to do is I'm just going to call this, so let w hat equal to w tilde and b hat equal to y bar minus mu transpose w tilde. And so what we have is that yi is about xi transpose w hat plus b hat, where we plug in these parameters. So what have I done here? Just to, like, recap what I've done, I know that if my x data and my y data were normalized, meaning demeaned, these equations are very simple to solve. It's very simple to solve for w and b. And so if I do that, then so if I standardize my data first, I can make these equations very easy to solve and just read them off. W tilde is equal to this, b tilde is equal to this. But that's for demeaned data. So what I actually have is not demeaned data. I have I have this equation that, like, yes, so my predictor for y tilde I is going to be xi minus mu transpose w tilde. But then, so what's my predictor for yi? Well, my predictor for yi is y bar plus xi minus mu transpose w tilde. And then I just plug all this in. So my estimator for yi is then just going to be xi transpose w tilde plus this offset. And then that is the new offset. And so what we see is that the optimal w hat is just this w tilde that I solved for when I demean my data. And then the b hat that I have to estimate that yi is just this quantity that came out of this process of demeaning. So you first demean your data, you solve for w tilde and b tilde, and then you plug in, you find out what they should have been if there was no offset data. Okay. Any questions on that?
Teacher, I have a question.
Yeah.
Can you just scroll up? I have a question on the equation set. Like, based on what condition or assumption that you wrote the equation set to solve the W tilde and the B tilde? Why these two equations are strictly equaling left hand side and right hand side?
You mean how did I get
confused
these?
about the equations.
How did I get these?
Yeah, how do you get the equation?
Okay, so these are coming from, Jamie went through this in her lecture. So I'll go through this kind of fast. Look back to hers for more, but basically, it comes from the fact that I can write, oh, it didn't do it. Oh, I see. I think it breaks every time I try to add a page. That's pretty not great. So this is equal to this, where I've just stacked again. And now, so if I take the derivative of this guy, this is equal to, if I expand this out, so yeah, if I take the derivative of this guy with respect to w, I get 2y minus xw plus b1, and then transpose x. It's on this side. And then so it's as a derivative of the w, that's gonna have to be equal to 0, but that's just equal to 2 x transpose y minus x transpose xw minus x transpose 1 times b. That's all equal to 0. And then so what we get is that for rearrange, x transpose xw divided by 2, doesn't matter, plus b x transpose 1 is equal to x transpose y. That's what w, and that's exactly yes, that's exactly what we got. And then if you repeat this exercise for that expression, doing with respect to b, we get the same sort of thing. Whatever the expression is over there.
Yeah, thanks.
Yeah.
I understand that.
Thanks.
Thank you.
So that's the first way of doing this. And now there's a great question about like, well, wait a second, what's this whole business about appending a column of ones? So let's talk about that. So let's say I want to fit, I have my data, x, I, y, I is equal to 1 to d, and I want to fit wb such that yi is about xi transpose w plus b. Now, another way of thinking about this, right? Because xi transpose w, what is this actually? This is really just like xi1 dot xi transpose w wd plus b. But then I can write this in a funny way. Like, well, I can also think of this as like 1 times b. And so this is also, I can write this as xi1 dot 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 xid 1 w1 dot 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 wd, and then b like that. And then I can define this as being like a new transformed version. And I'll define like that, I guess. X, we're defining this guy as xi transpose, and I'll call this let's say w, like that. And now what I see is that I basically become linear again, which is really nice because we know how to do that, right? Because now all I would do is I'd map my xi's all to an xi by appending rows, by appending a 1 to the end, and then w by inflating dimension by 1. And then we would just solve the linear equations just as we did. Because now what we want to do is we would say, like that. Another way of doing, and appending another row of 1s is equivalent to just having, let's call it that, x, comma, 1, just appending a row of 1s. Because now this is equivalent to y minus x squared. Which is a little nicer. Okay, so these are 2 strategies to overcome these offsets. Okay, are there any questions on this? These are the 2 different strategies to deal with offsets. You can use both, and so in your in that homework problem, it's saying append a row of 1s to deal with a constant offset. So it's doing this strategy, the second strategy, but it's also saying please standardize your data though. You still want to standardize your data, and so what that's saying is because this issue of like things are going feet versus inches, you're going to standardize your X matrix as we did above, but then you're still going to append these rows of 1s. And so that's what I'd really suggest you do in practice is whenever you're running a linear regression, you first standardize, you get your features, you subtract off the means, you divide by the variance in each dimension. We'll get other strategies in the future. And then you append a row of 1s, and then you just do linear regression on these coefficients as if it was completely linear without an offset. Any questions?
I had a question.
Yeah.
Right. So the fact that you wrote, like the prediction that you get from like after, so you're assuming that the prediction that you get after mean subtracting and standardizing, like you're assuming there, you said that like the mean and variance don't matter, right? Of the data have no effect on the prediction.
Yeah, they give no predictive power. Yeah.
Yeah. How often is that true? Like,
it's completely data dependent, and that's why standardizing data is a good rule of thumb. But it's not always the right thing to do. Like, especially if your data is like always positive. For instance, if it's like dollar amounts or something, like that might be a really bad idea. Or like, so it's very dependent, or like concentrations. Like, who knows? Like, there's lots of examples where demeaning your data would be a really bad idea. But it's very domain specific. And that is part of machine learning, is like being an engineer and looking at your features and understanding them, and not just throwing it into a DeepNet or XGBoost, but like actually thinking about what your features are and transforming them and to begin with, so that they make sense.
Mhm.
Okay, any other questions? All right. Okay, so I didn't really plan on spending the first 30 minutes talking about this, but it's okay, because I think it's useful. And we also are going to talk about ridge regression next, which is very relevant to this. Sorry, we're off my screen. Where'd you go? Where'd you go? Okay, so last time we talked about bias-variance trade-off and overfitting. So I just want to review that real fast. We had this very simple model where we had different function classes, like cal f is like all degree 1 polynomials, f2 is all degree 2 polynomials, f3 is all degree 3 polynomials, and I'm assuming that that includes all polynomials below it as well. And then for each one of these classes, f1, fk for k equals 1, 2, 3, 4, etc., we're going to define f hat k as basically the f within fk that has the lowest training error on our data set. We observe some training data state D, and we got the lowest training error on that training data, but constricted, but just within this function class of fk, like only degree k polynomials. And we did this for all k. And of course, complexity is growing with k. So we can do this. We can look at the training error. That's a number that we can compute. We get an f hat k with a minimizer of this training error. We can look at what that number is. But of course, we only care about the true error. We don't care about the training error. And what we saw was that the test error is an unbiased estimate of the true error. We expect that to be very close if the test data is completely independent of the training data. And what we see is this characteristic U-shaped curve of the training data, of the test data. When complexity is very, very small, down here, you have very large test error because the true error is very large. Because if the truth is, say, degree 7 polynomial, then basically you're underfitting. You don't have enough complexity in your function class. If the true degree polynomial is 7 and you're fitting a 3 degree polynomial, you're never going to fit that data accurately enough. So if you're not complex enough, you're getting too much error. If, on the other hand, if you have too complex of a model, if the truth is a degree 7 polynomial and you have a degree 50 polynomial, then what's going to happen is that you're going to fit every single data point of your training data very, very closely. So it'll be perfect. You'll get almost zero training error, which is what we see is your complexity increases. Your training error is always going to monotonically decrease. But essentially, if you're too complex of a model, you're basically just chasing noise. And that is what translates into variance. And so eventually your test error is going to start going up again. And so this test error, so these are two characteristic sort of shapes of how your training error and test error behave. The training error is typically always monotonically increasing with respect to complexity. And the test error starts high because you're not complex enough, dips below as you get, as you maybe hit around the degree 7 polynomial, the truth down here, or lower. But then as you go up and you increase that degree of that polynomial past the point of being complex enough, then you're just sort of fitting noise and you're overfitting to the data. And this is translating into variance. As we talked about yesterday, this test error is an unbiased estimate for the true error. And the true error decomposes into these three pieces of irreducible error, bias, and variance. And the bias portion is typically the first part of this downward curve of the test error. And the variance is responsible for this upward tick at the end. And what you want to do is pick the point that balances these two behaviors at the minima of this thing. And basically you want to hit this point that minimizes the error on the test error. That's what complexity, that's the degree polynomial that you want, because that's an unbiased estimate of the true error. And so the training error is a very, very bad metric to look at in terms of how well am I doing, how good is this estimator, because it's always going to be an optimistic look at how you're doing. Basically, the error rate, the expected training error will always be less than the expected test error. And so never report the training error to someone, they'll laugh at you because it doesn't mean anything. It really only makes sense to report the test error. And it's critical that the test set and the training set are completely disjoint. There's no overlap between the training and test set. If you say that you're reporting some test error, but you use some of that test data to train or pick hyperparameters or something like this, people will laugh at you and they won't trust what you're saying. You really need to keep this test set locked up, and you never sort of look at it until you've already picked your model, you've picked your K, and now you just want to report the test error to your boss. And so, yeah, this is all this is saying is that you use your training data to learn a predictor f hat K and pick K perhaps, and use your test data to report the predicted performance. You're never actually going to use your test data to choose what K or what training to do. You're only using your test data to report performance. And you can only look at it once, essentially. And so the big question is, how do you use your training data to pick the complexity K? And that's what we're going to talk about in this lecture. The question of like how do you distinguish, or how do you decide how big to make the train test split? This is something that is problem dependent, but typically you want the test set to have, you know, as many samples as possible, but like typically a 90-10 split is pretty appropriate. 90% training, 10% test. If you're just given a data set, you have to make a train test split. But typically, you know, if your data set is very, 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 very large, that's sort of ridiculous, because at a certain point, the law of large numbers, or CLT, kicks in, and you really don't need, past a certain point, adding more points to test it doesn't really help. And so this is typically around a number of like 10,000 or something is when it starts to become pretty reasonable. Okay. So how do we control this bias versus variance trade-off? What we already saw one example of degree polynomials, degree K polynomials, where as you increase K, the bias decreases and the variance increases. That's one way we can control bias and variance. These linear models. This is an example. There's also many other ways to control bias and variance. And one of the biggest ways of controlling this trade-off is through a concept known as regularization. And at a high level, regularization is a means of, in the face of indecision, or in the face of many potentially equally good options, regularization will bias you towards a solution that you, as a domain researcher, feel is most appropriate. Meaning that if you have, you know, if you're running, if you get, basically you run some loss, some training procedure, and you get 3 possible answers out, and they all have the same training loss, for instance, then which one is best? And basically, regularization helps to choose automatically the simplest one, where simple is problem dependent and how you will define simple. And so we'll see a few examples of this over the next couple lectures. But the first one is known as ridge regression. So recall least squares, where we've just been talking about this entire lecture, without an offset for now. And now, what we saw is that when x transpose x is invertible, we can compute x transpose x inverse x transpose y, and you can get the solution out. This is just the solution to this problem. But sometimes x times x is not invertible. What do we do then? Well, what will that do? If you're underdetermined, we know that, like, well, we're really needing to solve, where this comes from is w hat ls satisfies x transpose x, w hat equal to x transpose y. W hat is the minimizer w hat. If w hat satisfies this relationship, then it is a minimizer of your training error. This comes straight out of these equations. But if x transpose x is not invertible, many w's satisfy this relationship. An infinite number actually satisfy this relationship. Because basically, if x transpose x is not invertible, that means it's not full rank. And if x transpose x is not full rank, that means it has a non-empty null space. And the null space, of course, is of a matrix. A is a vector x is the null space of a matrix A if ax is equal to 0. So basically, if let's say if alpha is in the null space of x transpose x, then x transpose x, w hat plus alpha is equal to x transpose x, w hat for all alpha in the null space. And the null, this is non-empty, not empty if x transpose x, if only if, is not invertible. So because of this, this means that there's it's not unique. There's many w hats that are minimized with this training error, and we need to pick one. And so you could just pick any one, but it's pretty clear that some are more probably right than others. And so let's think about this in terms of pictures. So this expression, if we think about what, ignore all this. You don't need to see this. If you just look at this expression here, the sum of losses. Okay, if you just look at this loss function, the sum of y minus xi transpose w squared, if you look at each one of those terms, okay? So this is difficult to visualize, but suppose you're in 2 dimensions, right? If you're in 2 dimensions, we have each one of these w's, we're in w space now. Basically, xi is pointed in some direction. And basically, you're taking the inner product with w, and now you're saying, well, what is the inner product with w minus yi, all of that squared? So basically, because you're always projecting w down onto xi, on a direction xi, and then subtracting something and squaring it, basically, if I look at something along this line, if I look at w, the loss of this guy, just one of these guys, the loss stays constant along that line. If I'm looking at this function and I'm looking at it from above, so w is in 2D here. If I'm looking at this function from above, then what's going on is the function value, if I keep at the same inner product of xi, it never changes. It's flat in that direction. So for any w where I'm keeping the same inner product with xi, which is all those points on this line, they have the exact same function value, this thing squared. And that's also true for any line on this line, right? And any line on this line. But then at a certain point, it repeats and starts getting warmer. And so there's sort of what you're thinking is like you're looking down at the function of y minus x transpose w, and this is really the surface, the lost surface of this. So another way to think about this is these pictures here, where if we're in 2D, the lost surface looks like this piece of paper where it's a cone, it's a quadratic, and basically it's in this direction pointing. Oh, this is difficult with video. It's pointing in the direction of the half pipe. Basically, the opposite, the orthogonal direction to the half pipe is the direction of xi. And then the direction of the half pipe, if you're going down the half pipe, that is the direction in which this function is flat. And so each one of these little terms, y minus x transpose w, is this function that is one of these half pipes, but they're in d dimensions instead of just 2. And what this means is that if you're in d dimensions, each one of these individual terms is actually flat in d minus 1 dimensions. And only what we hope is that if you have n greater than d points and you have they're all linearly independent so that it's full rank, we have that each one of these functions, even though each one is individually flat and the minimizer of it is not unique, when you add all of them up because they're in different directions, because my xi's are in different directions, the hope is that this adds up to some bowl-like thing that we can then minimize to. We will do our gradient descent or whatever and go down this bowl and converge to the bottom of this thing. Okay, and so each term in the sum is contributing a little bit of a half pipe, or it's a quadratic actually. And then we hope that when there's sum, because they're on all different directions, they're summing to something that looks like a bowl. And that's what's happening in this d-dimensional space, in this function space, that linear least squares is really just, if you think about the loss function, what does this function look like as a function of w? For each individual I, it looks like one of these functions. And then if you add all of them up, they're going to sum up to something that looks like a bowl. Okay? And I know that's kind of, if you've never thought about it like that before, pictures really help me. And so this is how I think about it. If you don't like this, then you can just look at the math and it will also work out. So the hope is always that you have n greater than d linear independent vectors, and it will sum up to something that is a bowl, and it will be a unique minimizer. Now, what happens if d is greater than n? Meaning that I have fewer examples than the dimension of the space. In that case, if we formed our least squares problem, I'm saying that X is an n by d matrix and n is less than d. That means X is not full column rank. And that means X transpose X is not invertible. And by the last discussion, that means that the minimizer of this is not unique. There's an infinite number of W's that minimize this expression. So which one do we choose? And so this will happen every time d is greater than n. If you have more features than you have examples. And this is kind of scary because it's not unique. And if the solution is not unique, then there's nothing suggesting that the W that you get out of this procedure, if you run, say, if you would run some minimization procedure, you put in some black box minimizer program where you run gradient descent like this, there is nothing that says that the norm of W, that W, the components of W should be small or anything. they could absolutely go to infinity, because of this property that alpha, if alpha is in the null space of x transpose x, alpha can be arbitrary magnitude. Alpha can be a vector in the null space, and then you have a length of infinite, and it just would not change this. And that's really bad. It's really bad intuitively, because in the face of, indecision, or the face of not having any preference towards one solution or another, it seems like a bad idea to put a lot of weight on something that you don't really have any real reason to do so. And where this comes up is if, think about if you have a lot of data, if you have some data, but d is less than n, or around that range, and it's pretty noisy. There's a little tiny bit of noise in the features. Now, what you like to do is, if you see a new feature that comes in, and it does have some component in that alpha direction, in that null space, you have no knowledge in that null space. You have no knowledge of what's going on. And so what you'd really want to do is, because you have no preference in any one of those W's, but you haven't seen anything, it seems better intuitively to estimate basically 0 in that direction than infinite, or some large value. Because what you'd like to do is, because you didn't learn anything in that direction. And so it's better to basically estimate 0 in that direction than estimate something enormously large, because each one of those both minimize the training error. And so to fix this, because we have infinite choices, we need to choose one. We need to choose the simple one. We are going to choose the one that has minimum norm. And so in the face of having all possible explanations, or in the face of having many, many possible explanations for the data you have, and choosing the simplest one is often referred to as Occam's razor. And one way of realizing Occam's razor is, choosing, in the face of many, many solutions, choose the simplest one, is to provide regularization. And one way of doing that is to provide some additional penalty to your loss function. So if our original least squares function was just this guy, and it was a sum of these sort of half pipe sort of things, and there was there's some potential for not having a unique solution, what regularization can do is, in the face of that uncertainty, it's going to add a penalty to bias yourself towards a more preferred solution, a more simple solution. And what ridge regression does is it adds a little bit of an L2 penalty. Okay, so what this is saying is basically, all things being equal, I prefer the W that has the smallest norm, the smallest L2 norm. So the distance, the smallest length of the vector W. Because given all possible W's, they all sort of fit the training data the same. I want to pick the one that has the minimum norm, which is a very reasonable thing. This is essentially what ridge regression is doing. It's penalizing W's that have very, very large norm W. Now, it is not doing exactly what I said a moment ago, just 1 second ago, saying that, all things being equal, I prefer the minimum one. This is actually penalizing all W's in all directions. So even in those directions where the function is not flat, it's still penalizing it a little bit. And we'll see that that's true, but it's actually, on the other hand, we can think of that as not being true, which is interesting. Basically, it's the theory of Lagrange multipliers, and we'll see what's going on in a moment. But typically, so what ridge regression is doing is, instead of just dealing with these flat functions, the some ambiguity, it is adding an additional penalty term to make this loss function unique. They minimize this loss function unique. It's penalizing large norm solutions, and so it prefers more small solutions. And so you can also think of this as a complexity regularization, because while I'm saying the easiest way to think about these things is when you have n less than d points, and these guys are not summing up to something that looks like a bowl. But in reality, if you've ever thought about this kind of stuff before, if you're familiar with an ill-conditioned matrix, what's really going on here, why we like ridge regression, is because even if you have n greater than d, it could be the fact that like this stuff isn't like 0 or 1. It's not binary. These vectors could be very, very aligned with each other. And in some directions, you may have very, very few data. And so if your data is biased in the sense that in some directions you've got a lot of data, in some directions you have very, very, very little data, while you might not have while your solution may be unique in the sense that when you add up all these functions, they add up to something that is a quadratic, they could be extremely, so instead of being flat like this, instead of being flat like these guys over here, the end solution, it could be extremely biased. So it could be something like, it could be bowl-like, I'm drawing the equipotential here, but it could be like super, super sliced, ill-conditioned like this. Which is basically, I'm drawing like, it's almost flat in these directions. It's almost flat. And the reason why this would be bad is that basically, if I'm thinking about this loss function, that is like really, really stretched in one direction, that means a tiny perturbation in my data, like W, the minimizer of this W, a tiny perturbation in my data, this function could change quite a bit. Like this function, a teeny tiny bit in my data, changing my data, can change the minimizer of this function a lot because it's just so sensitive in these directions. Because the function is so flat in this direction. If the function is very, very flat in that direction, that means that there's not a lot of data supporting curvature in that direction. And so each one of these functions is providing curvature in some direction. And if you have a very little data in a particular direction, you're lacking curvature. And if you're lacking curvature, that means that the function is very flat in that direction. And there's only a very, very few data points giving evidence to where that minimizer is. And if this is the case, then what will happen is that a very small perturbation of your data will result in the actual minimizer of that data set, that whatever random data set you saw, to move around quite a bit. What W hat you particularly get on any given run will move around a lot. And we don't like that. That is the very definition of variance. Meaning on any particular data distribution draw that you get, the minimizer of this function could be wildly different each time. That's the definition of variance. What we'd like to have is that for any given draw of the data, the minimizer of this function is like more or less in the same location. And that is exactly what ridge regression does. It adds a penalty, an LT penalty, so that these flat regions or almost flat regions, we add some curvature and say, look, all things being equal, I don't really trust this flatness here. Like that kind of scares me, because I know like a tiny perturbation of my data could have really changed that quite a bit, the angle of that. And so I'm going to add this L2 penalty, this bowl, and explicitly add a bowl multiplied by some constant lambda to prefer more simpler solutions, so that when I get every new data set, the W hat that minimizes this sum of both the loss functions and this penalized norm will be basically the same every time, or closer to the same. And so this lambda is very explicitly playing the role of complexity. As lambda goes to 0, you're not penalizing the solution at all. As lambda goes to infinity, you are basically, this function is now going to dominate your actual loss functions. And so if you're penalizing yourself towards the minimizer of just sort of this penalty term, then that's the simplest possible solution, but it's probably wrong. Meaning it probably has very high bias, but it will have very little variance. We'll see this in a moment. But first, I just want to go through, how do you actually solve for this thing? And fortunately, it's very easy. It's very easy because we've already solved our least squares. We can write our least square solution out in vector notation like this. And so we know what to do. We take the derivative, rid of the gradient, so it's W. And that's going to be our friend. And just 2 x transpose y minus, oops, we got minus here, xw plus 2 lambda w. And now we're going to, this is going to be minus 2 x transpose y plus 2 x transpose x w plus 2 lambda w. I solve for w. And what I get is that I divide by, I solve this, put this equal to 0. Get x transpose w is equal to x transpose w plus lambda w is equal to x transpose y. And now I'm going to combine these terms as equivalent to saying that x transpose x plus lambda identity w is equal to x transpose y. And these are equivalent, of course, because identity times, some vector z is always equal to z. So I'm just saying that identity times w is equal to w. And now what we see is that we can read off the solution that x transpose x plus lambda I inverse, we just take the inverse of this guy, we multiply by the inverse of this matrix on the left side on both sides. And so we get that w hat is equal to x transpose x plus lambda identity quantity inverse times x transpose y, which is just this guy here. Now, I want to give you some intuition about what's going on here, right? Because what we're really doing is we were worried how we opened up this section was saying like, well, I'm worried that x transpose x is not invertible. I'm worried that x transpose x does not have that it has a null space. Now, when I add lambda identity to x transpose x, it no longer has a null space. For any positive lambda, I'm assuming that lambda is greater than 0 here. For any positive lambda, x transpose x plus lambda is a full rank matrix because identity is a full rank matrix. And x transpose x is something known as positive semi-definite, and lambda I is positive semi-definite, and so these matrices they won't cancel or anything like that. We'll talk more about that in the future. I don't want to get into definition of positive semi-definite right now. So what you're really doing though is basically very explicitly, you can think of x transpose x as being like describing the curvature, and lambda I is really adding more curvature. You're very much just like adding more curvature to your problem. And so I want to give you some intuition. So like, suppose that x transpose x is equal to n times identity. When would this be true? Almost never. But like it's a proct. You could imagine that you normalize your data. There's ways to normalize your data so that this is approximately true. Those are large n limit, the off diagonals will be with some particular normalization schemes. The off diagonals will be basically 0, and so this is sort of a very hand wavy sort of like just assume that x transpose x is good at n times identity. Don't ask when this is true, but just assume you're in this situation. Now, and then you assume, you're also asking you to assume that there exists some true w such that the y's you observe is equal to xw plus epsilon. And epsilon is equal to, is drawn from a Gaussian distribution. Then the question is for any particular x and a random y drawn from our model, x transpose normal x transpose w variance sigma squared. We could ask the question, like we were asking in this bias-variance trade-off, like we were in the last lecture, of what is the error, right? I'm going to solve my w hat ridge. I'm calling for ridge regression. I'm going to solve this w hat. I'm assuming this model is true. And I can ask, okay, well, how well is my error going to work? This was the topic, analyzing this piece was the whole topic of bias-variance trade-off. And so let's go ahead and do that. As we saw last time, we saw this error decomposes into the irreducible error and the learning error, the irreducible error being the sigma squared. Okay. And then those two pieces decompose further into the irreducible error, the bias squared, and the variance. Okay, and I plugged in what these values are for our particular model here, these linear models. And now we know by definition how we saw this, W hat is equal to this equation. By assumption, we have that Y is equal to this noise model, XW plus epsilon. So we can actually solve for W hat ridge in closed form. This is the definition of W hat ridge. Like this is, if you plug in our model and what the regression solution is, this is what W hat ridge is. It's just given as this expression. And so we automatically see something that happens here, right? This is the solution of W hat for our particular setting. And what we see is that lambda, as lambda goes to infinity, so lambda is this penalty term we're adding, as lambda goes to infinity, what do we see? Well, this first term, well, they both go to 0, right? W hat ridge goes to 0. And that makes total sense because as I'm adding an L2 penalty, so if my L2 penalty gets, if the lambda times the L2 penalty goes to infinity, it's going to ignore all my loss functions and it's just trying to minimize lambda times the L2 norm of W, but that's of course going to be 0. So it's intuitive that as lambda goes to infinity, this is going to, W hat is going to go to 0. And then for any intermediate values, it's doing something else. But W here is the truth, right? W here is the truth. And so what lambda is doing, you can think of it as sort of, lambda is shrinking the solution away from W towards 0. It is W is the true W. And what ridge regression is doing is it's shrinking, it's just multiplying W, the true W, by some constant that's less than 1, because n plus lambda is less than 1. And so if lambda is much less than n, then this isn't doing all that much. If lambda is much greater than n, or on the same order, you're shrinking W quite a bit. But one other thing it's doing is it's also shrinking the noise. And because the second term doesn't have an n in the top, it's actually shrinking the noise by quite a bit. And so this is, intuitively what's going on with W hat ridge. But what's really great is that if we plug this value of W hat ridge into these equations that we just derived here, we can get closed form expressions for what the irreducible error is, what the bias squared error is, and what the variance is. And so now what we see is we're getting an explicit characterization of what the bias, the variance, and the irreducible error is for this very particular model. And now you can verify these equations at home. It's a good exercise, but I'm not going to go through it. Now, what's super interesting about this is that we can explicitly look at this and be like, oh, wow. Okay, so what's going on here? As lambda goes from 0, if for lambda is equal to 0, there's no bias, right? Because lambda squared over n plus lambda squared, that's equal to 0. Okay, so when lambda is equal to 0, we have the least squared solution, and the bias is equal to 0, which is exactly what Jamie did last time. She showed that the bias of least squares is equal to 0. So okay, great. We're backwards compatible with least squares. That's good. But then as lambda gets large, as lambda gets off to infinity, this first term, say as lambda is much larger than n, this first piece here is going to go to 1. And so our bias squared is basically this W transpose X squared. That's very intuitive because W is the truth. And what is the bias telling you? The bias is saying, how far off are you from the truth? The expected, how far off is your expected answer from the truth? Well, you're going to what we just said on the last slide is that if lambda is very, very large, you're just going to output W hat equal to 0. If as lambda goes to infinity, W hat is going to be 0. So if W hat is 0, the bias of your estimator is just going to be the difference between what you output and what the truth outputs, which is just W transpose X quantity squared. And so this is very intuitive that this bias squared is exactly how we'd expect. For lambda equal to 0, there's no bias, there's 0 bias. But then as lambda gets very, very large, it saturates as this W transpose X. And so what this looks like on a plot, if we try to plot this is lambda, or we'll do as lambda, so for lambda very, very small, the bias is 0. And then, so it stays down here, and then as lambda grows, the bias increases, and then it saturates. And it saturates at this W transpose X squared. The irreducible error, of course, is just a constant. And the variance, let's think about the variance now. For small n, for lambda equal to 0, this variance is some constant term. It's whatever this term is, d sigma squared n over n squared. That's if you plug in lambda equal to 0. But as lambda goes to infinity, of course, the second term is going to go to 0. So now the variance is actually acting like some big value over here, and then it actually goes down, and then eventually goes to 0 as lambda goes to infinity. And so the total error is the sum of these three pieces, obviously. And just from this picture, it's pretty obvious that the total error is minimized at some sort of particular value of lambda that's not equal to 0 and not equal to infinity. It's some value in the middle. And what's amazing about this is that for any amount of data you have, for any value of n, any finite amount of data, it is better to choose a non-zero value of lambda than to use a value of lambda equal to 0. Meaning that, like, ridge regression, what this is proving is that ridge regression for some non-zero value of lambda is strictly better than least squares. Always. There always exists a value of lambda that's non-zero that will improve over least squares, which is really kind of interesting. This was actually a really big deal in statistics at the time when this was discovered, that like biasing yourself towards 0, like this weird thing. Why are we biasing ourselves to 0? The fact that it always helps to bias yourself a little bit, what kind of rocked the statistics world for about 50 years. It was a very, very big deal. And you can go into Stein's estimator and these sorts of things. I can post some historical stuff if you'd like. But like, it's actually a really big deal that adding bias, this story is actually much deeper. It's just very cool. But anyways, ridge regression, great idea. Always helps. And so, and I want you to have intuition. So let's have a little test here. So the solution is indexed by the regularization parameter lambda. And we went through all these calculations. You know, we looked at what the solution of W hat ridge is under these conditions. And now, and we looked at this bias and variance thing. And this is sort of the idea, the intuition that I want you to have. But all of these can kind of also be gained by just looking at the loss function. Because as you increase lambda, you are penalizing the solution. You are biasing yourself towards some other solution, and namely biasing yourself towards 0. And so as lambda gets larger, the bias does what? So as lambda increases, what does the bias do? Decreases. Or sorry, increases. Sorry. The bias increases and the variance decreases. And the intuition there is as lambda is very, very large, this is the only part that really matters. If for lambda large enough, this second term, the penalty term, is going to totally dwarf the first term. And so you're really biasing the solution. You're not basing it on data. Data is what makes it unbiased. and you're biasing your solution towards some particular value, which is 0, but you're biasing your solution. Now, because you're biasing your solution, you're sort of ignoring the data earlier. You're putting less emphasis on the data and preferring lower norm solutions. By doing that, you are thereby also decreasing the variance, because you're not going to chase, you have sort of added more curvature to this problem, so that if there is some spurious xi or yi, you're not going to start chasing and try to follow that exactly. You're going to minimize the norm of this w that it can be. You're trying to reduce the size of the w if at all possible, so the variance will decrease.
And this reminds me, I think somebody asked during my lecture, like, why would you ever pick a biased estimator, right? Why would you ever pick an estimator whose bias was not equal to 0? And this is a great example of why, right? By increasing your bias some, you can decrease your variance by a lot, and that's sometimes the thing you want to do.
Exactly. Thank you. And then, so just to finish up the slides, lambda goes to 0, w hat ridge goes to w hat the least square solution. And as lambda goes to infinity, w hat ridge goes to all 0 vectors. And that's obvious from just looking at this objective function. So lambda goes to infinity, it's just going to ignore the first term. And so it's going to be somewhere in between. So really what's happening is that regression is somehow interpolating between the least squares and estimator and 0. It's shrinking the estimator towards 0. Now, intuitively, going back to this picture of bias variance, instead of having k, these nested classes of fk, we can think of this complexity class as a continuous sort of parameter, where the cal fk is actually where k is equal to 1 over lambda. So because I want like larger numbers to be more complex. So we just said that smaller values of lambda makes more complex. So 1 over lambda, larger values of 1 over lambda is larger values of complexity. Larger complexity. And so if we compute our w hat ridge for each value of lambda, if we computationally did that for every value of lambda, we saw for what the w hat ridge for that particular lambda was, and then we plotted the test error and training error, we would get a plot that looks like what we had before. And these curves actually came from ridge regression. I didn't tell you before, but this is where they actually came from. You'd get something where the training error as 1 over lambda gets very, very large, meaning as lambda goes to 0, you're getting the bias is going to 0, as we saw analytically on the last couple of slides. But the total error, the true error, the sum of the bias and the variance, first starts large with high bias, and then decreases. And then as 1 over lambda gets very large, or as lambda gets very small, you add more and more variance, and then you get this U shape where the minimizer of this is some non-zero value of lambda that trades off the bias and the variance. And one last thing is, like, what do these coefficients look like? In that simple example where x transpose x is equal to n times identity, that assumption, well, if x transpose x is not equal to n times identity, if it's something else, then in that case, it just directly shrunk all the coefficients the same amount. But when x transpose x is not, when you use some arbitrary data, it's going to do something else. Basically, it will shrink different components more than others based on the data. We'll talk more about this when we talk about SVD. But as you can see here, here's just an example from the Murphy book, whereas 1 over lambda increases as the complexity increases, what the coefficients actually look like of your weighted of your W. So that each one of these, so each line here is for a particular value. This is one value of lambda. And then each dot on here is the value of W, what came out of the ridge regression solution. This is actually looking at this where D is equal to 1, 2, 3, 4, 5, 6, 7, 8 here. And it's just visualizing these. And so as 1 over lambda is 0, so as lambda goes off to infinity, we have the intuitive solution that like, yes, it's 0. If lambda is equal to infinity, then 1 over lambda is 0, and you have all the components of W at just 0. But as lambda gets very small, the complexity increases, and you converge the least square solution, which is this, and in between is doing something else. And one thing I want to point out here is that they are not monotonic. Sometimes what happens is you trace this lambda, the coefficients do not always stay positive. They can go positive and negative, which is really quite unintuitive. So, okay, last slide here. Regularization is penalizing you towards simpler solutions, preferred simpler solutions. This was the L2 penalty. There are many, many other kinds of regularization. We'll see another kind next time that will be very interpretable. But what I want you to sort of think about is just one form of it. Regularization trades off this bias-variance trade-off and can control basically how much you're overfitting to the data. And if you're overfitting, one way of doing it is to regularize your solution towards something simpler, and that controls the bias-variance trade-off. However, what I've not told you is how to pick this lambda, because you're not allowed to look at the test set to pick this lambda. And that's what we're gonna talk about next time when we talk about cross-validation. Okay, thanks everyone. Sorry I went over, and I'll take questions for the next how long.
Teacher, I have.
Go for it.
All right, teacher, I have a question. For the can you go back to the previous slides that the true error, the predictor, the test error? Oh, yeah, this one. We were told here that it's important to keep there no intersections between the training set and the test set, and this condition can guarantees that our test error can represent the true error. In other words, the expectation of the unknown data.
Yes.
Why this logic is true? And I didn't remember any discussion on the proof of this logic.
You're going to prove this on your homework, actually.
All right. All right.
Because the x and y here in the true error are being drawn from the pxy distribution. And so now if I get IID samples from pxy and you take the empirical mean, basically all you're really doing is you're getting an IID sample and you are from this distribution. And we know that if I keep averaging those samples, that will converge to the true mean. And that's all this is really saying, is that like, it looks fancy because there's all these squared errors and those sort of things, but really what you can think of is just that like at a high level, you're getting numbers from a distribution. So one-dimensional distribution, and that the average of those numbers is the mean, is the expectation, which is this guy. And we know that if I just draw numbers from a distribution, if I average them, they will eventually, the empirical mean will eventually converge to the true mean. And that's all this is saying. That's why the test error is an unbiased estimate of the true error, but it's really nothing more than applying the law of large numbers.
Okay. One more thing to follow up is that since we need to keep there are no intersections between the training set and the test set, so when we are drawing the samples, like when we are drawing samples from the joint distribution of x and y, do we need to purposely avoid when we pick the samples that's already in the training set, do we need to use it or do we need to drop it?
So typically what happens is you never draw samples from PXY typically. You just have like Zillow house prices. You have, you download some data set from Zillow and it's never labeled as training and test. You just have the data set. So
sure,
what you would do is you'd split this data set up into 10% training, 10% test and 90% training. You basically do that once, put that test set in a file on your computer somewhere and forget about it, and then just use training to do everything you want. You do anything you want for the training data set, anything you want. And then only when you're saying, okay, now I'm going to sell this back to Zillow, this estimator. Only then do you evaluate your model on the test set. You do that once, right before you give it back to them.
Yeah, thanks. Yeah, thanks. Right.
Hi, Kevin.
Hi.
Oh, sorry. A quick question. Following that question, previous question.
Okay.
That is, why do we require there's no intersection between the training sets and the testing sets?
So if there's any intersection between the training set and the test set, it's this guy right here. So what are we using?
Right.
We're using the fact that for any fixed W, like if I just if it wasn't W hat trained from the training data, if this was just some fixed W that has nothing to do with the training set, then this would always be an unbiased estimator using the test or the train. Either one is fine. But if you now, because it's an IID sample, but if there's any overlap between, if there's any sort of the training set in the test set, now what's going to happen is that if I take the expected value of this, you now have this issue where the xi is one of these xi's is potentially from the training set, and this w is also from the training set. And so now they're dependent. And I can't just ignore the fact that w was just some fixed w. It's not just any w. It is, these are now dependent. I can't actually, when I take these integrals, I can't just pretend they're completely separate.
Oh, got you. Thank you so much.
And so like I think you'll go through this. There's an exercise on the homework that when by forcing yourself to go through it, it will, I think it'll elucidate some of these ideas. But if not, I would look up independence and things. I think Murphy has a good section on this.
Okay, got it. I will try that. Thanks.
Kevin, so you said that like so I guess that I'm like a little like mind blown about like the fact that it's provably better to use like, you know, like, are you interpreting like basically the reason why you're saying is it because say, you know, I have no knowledge about Bias-Variance Tradeoff. Basically, if I like you know, you have that, you derived the expression for the error, right? So if I basically like plot that, right, I fix my n, I fix everything, and if I just literally like change my lambda, and if I plot that, basically I will see like a parabola. Is that how you're saying that it's provably better?
I'm saying that so this phenomenon is known as Stein's paradox. And basically what it says is that if you add bias here, like if I give you n numbers, okay, forget about x's and y's, whatever. If I have n numbers, and now I'm trying to estimate the true mean of the distribution from which these numbers came from. Okay, what I'm saying is that adding like the empirical mean is like intuitively the only thing that's even reasonable to do here, because these numbers can be anywhere. The mean can be anything. The mean of these numbers could be 1 million. The mean of them could be -2 million. It could be 5. It could be the mean of these numbers could be 1 e to the -6. But somehow, the Stein's paradox is what's so bizarre is that there, for any set of numbers, if you bias yourself towards 0, if you do this ridge estimate, so like explicitly what I mean by that, so what Stein's paradox says is that if you have xi, so yeah, x1 ... xn drawn from some distribution p, where each xi is in R, okay, and the mean of x1 is equal to mu. So it has some expectation. It exists. Now, the unbiased estimator for these numbers, and of course, just the empirical mean. is just equal to 1 over n.
Yeah.
I equals 1 to n of xi. And now, because we made these numbers can be anything. They can have any mean at all. So like, it seems bizarre that biasing yourself towards some solution would ever help. But what's really bizarre is that if you have mu hat, we'll call it lambda, equal to, which is so. If you solve this problem, then there exists a lambda greater than 0 such that the expected error of mu hat lambda minus mu is always strictly less than expected value of mu hat minus mu squared. And so this is why this is so weird is that you've assumed nothing about the value of mu. Mu could be anything. And so like what this is doing is it is very explicitly, if you solve what mu hat lambda is, it is explicitly biasing you towards 0. That is equivalent. It's equivalent to saying like I just added a bunch of xi's to my data set that were equal to 0. Like that is a completely equivalent way of thinking about this. And so it's called a paradox, but it's just like, wait a second, I'm just adding an arbitrary number that happens to be 0 to my data set. And for some reason, for any set of xi's with mu, it's better to do that. It is a strictly better estimator. And basically, the reason why, it's not really a paradox, of course, it's bizarre. So the actual paradox here is that this is an inadmissible, the empirical mean is an inadmissible estimator, meaning that it's not strictly better than any other estimator at all times. This is what's rocked the statistics world for a long time, that biasing yourself towards this weird thing was always going to be better. And it's really cool. And it has everything to do with bias and variance. You are reducing by biasing yourself towards some number, which happens to be 0 here, you are biasing yourself. By adding a little bit of bias, you're taking away a little bit of variance. And it helps because I've assumed nothing about mu, I could translate my data. I could translate my data to already thing, and that's equivalent to adding some other number. Like if my data was truly mean 1 to the minus 6, it's like this is biasing yourself towards 0. I could bias myself towards the number 5, which is nothing to do with it. But there is a non-zero lambda that makes that true, which is just absolutely crazy. So look up science paradox.
Okay, thanks.
Regression is extremely related to science paradox. It's basically you look at it's like Tikhonov regularization, science paradox, science estimator. Regression is basically the natural extension to linear estimators from this simple one-dimensional example, and it's always a better estimator.
Can you also like kind of provably show this for like other like regularization, like L1, et cetera, et cetera?
That's a great question. I don't know. I would think so, but I don't know for sure.
Okay.
Yeah. Kevin?
Yes.
I have a question. Yeah.